Yes. So the next presenter is also from UTS, Dr. Yancheng Li.
Thank you, Lee. Great to be here to present our research. Yeah, so our topic, our project is basically try to quantify the crack, which I think everybody heard in this session, like from Dr. Yang Zhou here, why drone is so good to basically monitor the inspecting the bridge structures, etc. So we are zooming to small details about how we quantify the crack length, crack width, and some possibly crack depths in a sense to help us to use it further to evaluate the structural capacity or maybe decision-making process. So first, acknowledge the phone support by SmartCrate, Shandong High-Speed Group, and Concrete Pipe Association of Australia Asia. So here's the table of content. Briefly, of course, the traditional way of crack detection or inspection involve highly skilled inspector on site, which subjective can be depends on your skill and knowledge, and also can be a safety issue, safety concern in terms of you have to put people in a quite risky location, and also you may have to stop the traffic sometimes to bring the vehicle on site to which not that efficient in a sense. But also for traditional image processing technique, which involve a lot of challenges, which sometimes you have a water stain, you have a covered with plants, green plants, with handwriting. Sometimes it's graffiti, so it's very common here in Australia, right? And even further, which is currently from one of the projects with Concrete Pipe Australia Asia, some real industry demands is more complex. For example, over here, even though we haven't really started this project, but I can show you some photos over here. So the background for this project was like, for concrete pipe, is very, very complex. Even though you have a CCTV installed in the pipe, but somehow the image processing technique used can lead to many error detection or errors. For instance, for concrete pipes, the regulation specify any crack with bigger than 1 millimeter, you have to spot it. You have to do the following process, and maybe you have to pull out. So the result from the current technique is like something in the image, for example, the spider web, the snail trail will be labeled as crack. So we need a better technique to identify the crack, maybe giving, for example, label the crack, quantify the crack with only width of 1 millimeter. So that's the challenge for the industry now. So of course, our entire roadmap was like starting from crack quantification, which we are doing something using this for this time, two different sources for information fusion, multimodality. We also use the public available algorithms like from Meta to train it. We're also doing the structural capacity evaluation in terms of residual strength, residual capacity using the public available experimental data or some data from empirical equations, also some data from a finite element analysis. We try to lead to further for assessment in terms of decision-making, risk assessment to give the industry some information for decision-making. So here today we focus only on the crack quantification in terms of to try to determine the crack width, crack length, or possibly depth from the image side. So generally, I think everybody knows deep learning, so I just skip these slides. And moving further, for crack detection, typically we have an encoder-decoder structure, which you have. This is typical UNet structure. So this is the input. We have image. Going through the whole process, you will have the this segmentation. Basically, label the crack in pixel level. Try to tell them, okay, where is the crack? How wide is the crack? How far is the crack? So it normally involves a convolutional layer, batch normalization, activation function like ReLU, GLU, and then decoding, which you have deconvolutional layers. And somehow you have max pooling, which I will introduce later, try to reduce the computational requirement. Oh, sorry. Yep. So for the crack image, you basically involve different level of grayscales in the crack. Crack is much darker. The background is normally lighter. So by analyzing the difference between different pixel level, you can basically identify where the crack is. That's the whole principle. But you probably we involve downsampling, reduce the size of the image, and also try to abstract feature from the image. So this involves the filter, which you can see. You can, if you want vertical feature, you have this, one example for the matrix to kick in. If you want horizontal feature, you have this matrix to kick in, the filter. And for pooling, basically try to reduce the computational requirement. In a sense, if you want to bring to the side, you have a drone machine, you have portable devices. Normally, you wouldn't have a large computational capacity in terms of NVIDIA GeForce 4090. That's probably not feasible. So we try to use the pooling process to reduce the computational requirement to make it more lightweight structure, etc. So now back to deep learning crack detection. There are different groups. First, it's only crack detection. Typically, you only look once algorithms. So you can basically box the crack area. Okay. Further, of course, this is probably not enough. We want to know the detailed shape of the crack. So we go to the crack segmentation, which you basically can label the crack pixel in the image, produce this result. But we need further, because here everything is in pixel, like in terms of crack length, crack width, everything is pixel. But we want convert into real dimension, physical dimension. So we need quantification here. We want to know the length, width, and perhaps depth sometimes to help the people or asset management to make further decision. Then challenging the crack quantification is, normally people are doing this way. In a public literature over here, you put a marker over there with standard size. You know the dimension. If you can count the pixel numbers of the marker, you can have the pixel ratio, right? The spatial ratio. But in reality, you can't really put in every marker alongside this crack, which is not feasible. Also, other technique is to have a laser sensor which you measure the distance from the drone or camera to the surface of the crack to convert the spatial ratio. But somehow this also has an issue because it depends on how you drive the drone. Either inclined or not pointing to the crack area, will lead to error for the quantification. Also, for current algorithm, they tend to smooth the crack boundary, somehow exaggerates the crack information, for example, crack width. And also this needs to be an automatic process. So our approach, which we introduce a camera, which of course probably somebody knows, is LiDAR camera. You have RGB information, which is the image, plus the depth information. So if you can combine them together, then we basically be able to have more detailed or more accurate result in terms of the crack, overall geometry. The idea is very simple. It's basically if you have a crack image, RGB, which normally people do, you have RGB data you put into the network, you can produce this crack segmentation result. But with help of this depth map, because for depth map, you basically have a lot of information on the distance from the camera to the crack area. So for this one, of course, somehow we exaggerate. The boundary is more clear than the RGB image. So we try to combine them together to fusion the information through our network. Then in terms of spatial ratio, to convert this pixel information into physical information, we use some algorithm like YuLu to identify the crack area. Then since we know the distance as well, we can basically quickly or automatically get this spatial ratio, then to get result of this crack length and width, etc. Also, because we have a depth map over here, we are able to basically calculate or estimate the crack depth, the visible depth, not the crack tips, because crack tips can be inside the structure, which we can't really see from the camera. So that's the whole idea. So we use the Intel RealSense camera, the LiDAR camera with the specs over here is quite high resolution here. You can see the output of this camera basically have a RGB image, the depth image. You can combine them together. Of course, they are in different resolution. We have to matching the resolution from two sources. Then this is a transformer block we proposed, which take two input, which including the RGB and depth. So in a sense, in the beginning, you have RGB for each sources. You do the different level of resolution, abstract features in different level, then combine them. For each stage, you basically have this RGB image input, then depth image input to this fusion feature fusion transformer block. Then you output over here, then do the decoding stage. Of course, this involves multi-stage of process over here, combine them together. We also proposed for the normal CNN model, because normally the model only contains one RGB input. We also have to modify them to adopt for an additional input, which is depth image. So try to similar process with fusion technique over here, and to hopefully improve the accuracy. This is some metrics. I think Yancheng did a very good job on introducing this one. So I basically focus on those 2 points. For this case, we only have limited data because we don't have public available data set. We only have 1,000 pair of RGB images and depth maps. And we basically here, we modify all the popular available algorithms, including UNet, DeepLab, PSPNet, etc. And also some swing transformer, transformer-based network, also we modify them to be able to adopt two source of input. Okay, this is the result. So for crack detection, the very important parameter is the MROU, which basically give you more indication in terms of how accurate your result is. So you can see from here, any algorithm with a star over here means we adopted this information fusion for RGB and depth information. Without this one means only RGB. You can see the improvement from the MRU is 3% normally. So we compare with each one. You can see for each individual network, if you only have RGB input and compare with two inputs, there's an improvement. Here we also propose our own thing because if we call it FFSEC former, so you can see the MRU is much higher than the other ones because we basically have this algorithm over here. So proposed with everything contained in the algorithm. Okay, so here is some images we have from the pavement because pavement is less challenging. We are also doing something more fun, crack, very thin crack in meantime now. On top is the result for crack. Here is zooming part. So the red one is false positive, which is not really a crack, but you mislabel as crack. Also, we have false negative, true negative. You can see from this result, because we are looking into the crack width, so this detail becomes so important for us. So we really look into how we can, minimum the false positive, try to improve our accuracy of the algorithm. I'll show the spatial ratio conversion here. We have ULU. We box the crack area. We basically measure the average distance except the crack area. So in a sense, we know the distance is more accurate. We can basically use the camera parameter and also the distance to convert to get our spatial ratio here to get a more accurate result. Here's some result. So we have this comparison, ground truth. This is ground truth for skeleton of the ground truth crack. And you can see from here, our approach is more accurate in a sense compared with the ground truth. And we also, to quantify the crack width, we basically along the crack length, a skeleton, we pick 100 points because you can't really do a manual measurement on the crack anyhow because it's somehow very thin. So we use ground truth as benchmarking in comparison with our result. So along the crack skeleton, we pick 100 point. So here, our parameter is 1 pixel equals to 0.1 millimeter for this research, but we did better. 1 pixel equals to 0.02 millimeter, so which means we can quantify even more finer or more thin crack with our algorithm. This is some overall overview for the result in terms of crack width measurement. The error is, this is a manual measurement. Manual measurement doesn't mean you manually measure. It's basically you measure the ground truth from your trained network. So our results are quite close to the result from the ground truth. You can see from here. In terms of crack length, we also have quite good error, quite good result from here. Error is sometimes only less than 1%, sometimes can be 4% in terms of length. For depth, of course, it's only the surface depth. This probably the maximum error we got is 10%, so which can give you quite good estimation in terms of crack width, crack length, and the crack depth. That's the conclusion. Thank you very much.